A star's final moments hold the story of our own creation. We often see them as silent, constant lights, but each one is a living entity with an emotional story of struggle and transformation at the edge of existence. This video pulls back the curtain on the most profound final acts in the cosmos. You will journey through stellar nurseries, witness catastrophic supernova, and discover the strange, beautiful remnants left behind. By the end, you will understand exactly how the violent death of a star billions of years ago made your own life possible. We will uncover what happens when a star's core turns to iron, and how the corpse of a giant star can become a city-sized diamond spinning furiously in the dark. What part of this cosmic story feels most connected to you deep within the cosmic clouds of a nebula? A silent gathering begins. Gravity patiently pulls together scattered wisps of hydrogen and dust, a process that can take millions of years. This is a stellar nursery, like the magnificent Orion Nebula, where the first chapter of a star's story is written. As this immense ball of gas contracts, the pressure and temperature at its core skyrocket until it crosses a critical threshold. With a silent, cosmic flash, nuclear fusion ignites. Hydrogen atoms are forced together to create helium, releasing a staggering amount of energy. This is the moment a star is truly born, switching on its light for the first time. It then settles into its longest and most stable period, known as the main sequence. Our own sun is in this very phase, a steady beacon fusing hydrogen into helium for billions of years. This is a delicate cosmic balancing act. The tremendous gravity of the star's own mass is constantly trying to crush it inward, but this force is perfectly countered by the outward pressure from the furious nuclear reactions in its core. For most of its life, this stalemate holds, creating the consistent, shining star we see in the night sky. Yet the star's ultimate destiny was sealed at its birth. Its initial mass is the single most important factor dictating its entire future. A relatively small star like our Sun has a very different path ahead of it than a behemoth many times more massive. This initial weight determines the intensity of the fusion furnace within, how long its fuel will last, and the spectacular nature of its final act. The stable, glowing life of a star is merely the calm before a storm of cosmic transformation, a quiet prologue to an inevitable and dramatic finale. But that stable, shining life cannot last forever. Deep inside a star like our Sun, a quiet crisis is unfolding. After billions of years, the hydrogen fuel at its core is finally running out. With no more hydrogen to fuse into helium, the nuclear fires that once pushed back against gravity begin to falter. The core, no longer supported by that immense outward pressure, starts to collapse under its own weight. This collapse, however, generates even more ferocious heat and pressure. It sparks a desperate, final act of nuclear fusion in a shell around the core, while the core itself begins to crush inward and heat up. The star responds to this internal rebellion in a dramatic way. It swells, expanding its outer layers to hundreds of times its original size. The star we once knew transforms into a red giant. Its surface cools, taking on a deep, ruddy glow, but its heart grows hotter and denser. This is the star's last stand, a final attempt to stave off the inevitable by beginning to fuse the helium in its core into heavier elements, carbon and oxygen. For any planets that once orbited comfortably in that star's golden light, this transformation is apocalyptic. The star's outer atmosphere, bloated and immense, stretches out to engulf the inner worlds. A planet like Mercury and then Venus would be swallowed whole, vaporized in the star's advancing embrace. Earth would likely share that fate, its oceans boiled away and its crust melted into nothingness. The entire habitable zone, the region where liquid water and life could exist, is pushed outward, radically reshaping the entire solar system. This is not a quick, violent explosion, but a slow, majestic, and utterly inevitable unmaking. The red giant phase is a poignant, emotional prelude. It is the quiet, swelling drama of a long, stable life finally coming to a close, setting the stage for the far more violent finales awaiting the universe's most massive stars. The star's final act of fusion is a fleeting blaze. Once the core has converted its helium into carbon and oxygen, the nuclear fires sputter out for good. With no more energy to hold it up, the star's core collapses one last time, compressing into an incredibly dense, Earth-sized ember called a white dwarf. But the star's story is not over. In its death throes, the star gently pushes its own outer layers away, shedding its vast atmosphere into the void. This is not a violent explosion, but a slow, cosmic exhalation. And what emerges from this release is one of the most breathtaking sights in the cosmos, a planetary nebula. The name is a historical accident, a misnomer from early astronomers who saw their round, greenish shapes and thought they were looking at distant planets. We now know they are something far more poetic. These nebulae are the final, artistic breath of a dying star. The exposed, hot core of the white dwarf, blazing at over 100,000 degrees, floods the slowly expanding cloud of ejected gas with intense ultraviolet radiation. This energy causes the gas to fluoresce, to glow with vivid colors. Intricate, often symmetrical patterns emerge, forming cosmic butterflies, glowing eyes, and delicate rings. The Ring Nebula and the Helix Nebula are famous examples, celestial sculptures painted across light years of space. This phase of transcendent beauty is heartbreakingly brief. A planetary nebula shines for only tens of thousands of years before it dissipates into the darkness of interstellar space. In the multi-billion-year life of a star, this is less than a blink, a final, brilliant flash of glory before the long, slow fade. It is a story of release and transformation where stellar death gives birth to temporary art. The white dwarf at its center will slowly cool over billions of years, a fading cinder. But the enriched gas from the nebula drifts away, carrying newly forged elements like carbon and oxygen out into the galaxy. This stellar legacy, this cosmic dust, will one day become part of new stars, new planets, and perhaps new life. The star's beautiful finale sows the seeds for futures yet to come. Left behind after the nebula's beautiful glow fades is the star's true corpse, a white dwarf. This extraordinary object packs the entire mass of a star into a sphere no larger than Earth. The result is matter crushed to an almost unimaginable density. Picture a single sugar cube of this material. If you could bring it to Earth, it would not weigh a few grams. It would weigh as much as a full-grown elephant, a crushing 5 tons or more, compressed into that tiny space. This incredible weight is the final, permanent victory of gravity. With all fusion ended, nothing remains to push back. The star's core is supported forever by a strange quantum mechanical force, a final, unyielding barrier against total collapse. This stellar ember is still searingly hot, blazing with the leftover heat from its billions of years of nuclear fusion. But with no new energy being created, its only possible path is down. It begins an epic journey of cooling, a slow fade that will last longer than the current age of the universe. It will glow white, then yellow, then red, like a forgotten ember in a cosmic fireplace. After trillions of years, theory suggests it will finally cool completely, becoming a cold, black lump of crystallized carbon and oxygen, a black dwarf. These dark cinders do not yet exist. Our universe, at nearly 14 billion years old, is simply too young for even the first white dwarfs to have cooled to absolute zero. This is the ultimate fate awaiting stars like our own Sun, a quiet, gradual descent into darkness and cold that makes even the lifespan of galaxies seem brief. The white dwarf is a monument to endurance, a diamond in the cosmic dark, holding the memory of a star's fiery life within its silent, super-dense heart. Yet this quiet fade is not the only possible ending. For a white dwarf locked in a gravitational dance with a companion star, a far more spectacular and violent destiny awaits. The white dwarf's immense gravity begins to siphon away the very substance of its stellar partner, pulling a stream of hydrogen and helium across the void. This stolen material accumulates on the white dwarf's surface, building up layer by layer over millennia. The white dwarf grows heavier, its internal pressure and temperature climbing with every bit of mass it steals. This cosmic theft continues until the white dwarf crosses a critical threshold, the Chandrasekhar limit. At this precise point, the star can no longer support its own weight. The core, now catastrophically hot and dense, instantly ignites a runaway nuclear fusion reaction. The entire white dwarf is consumed in a titanic blast, utterly obliterated in a single, furious flash. This is a Type Ia supernova, an explosion so brilliant it can outshine an entire galaxy. What makes this specific stellar death so crucial to our understanding of the cosmos is its remarkable consistency. Because every Type Ia supernova is triggered at that same precise mass limit, they all explode with nearly the same intrinsic brightness. This makes them perfect cosmic mile markers, what astronomers call standard candles. By observing how bright these supernovae appear from Earth, scientists can calculate their true distance with incredible accuracy. These brilliant, predictable explosions became the key that unlocked the scale of the universe, allowing us to measure the vast distances between galaxies and even discover the mysterious force we call dark energy. The violence of this explosion is a cosmic forge of incredible power. The temperatures and pressures are so extreme that they create elements far heavier than carbon and oxygen. In that fleeting, incandescent moment, the supernova synthesizes the iron in your blood, the gold in a wedding ring, and the silver in a piece of jewelry. It scatters these newly forged atoms across interstellar space, seeding future generations of stars and planets with the very building blocks of complex chemistry, and ultimately life itself. This is not a chaotic end, but a precise, predictable, and universe-calibrating catastrophe. It is a story of theft and resurrection, where a stellar corpse's final, brilliant act of self-destruction becomes a fundamental tool for mapping the cosmos and a primary source for the very elements that make our world and ourselves possible. The life of a truly massive star is a frantic, brilliant race against its own immense power. It burns through its nuclear fuel not over billions of years but mere millions. Its core becomes a frantic, layered forge, a cosmic onion with a terrifying secret at its center. In the outermost shell, hydrogen fuses to helium. Deeper in, helium fuses into carbon. The process continues inward, creating neon, oxygen, and silicon in successive shells, each layer fusing a heavier element to power the star's furious output. This chain of creation stops at the very heart of the star, where a core of iron begins to grow. Iron is nuclear ash. Unlike every element that came before it, fusing iron atoms does not release energy, it consumes it. For a brief, terrifying moment, the star's mighty engine has run out of fuel. the outward pressure from fusion, which has held the star up for its entire life, vanishes in an instant. And after millions of years of battle, gravity wins the war. The star's core, which can be as massive as our entire sun, has nothing left to support it. It collapses. It does not fall slowly. It implodes at nearly 1/4 the speed of light. In less than a single second, a core thousands of miles across is crushed into a sphere just a few dozen miles wide. This is the single most violent event in the life of any star, a sudden, total failure that sets the stage for a cataclysm so immense it can outshine entire galaxies. This is the prelude to a supernova. That catastrophic core collapse triggers a final, explosive rebound. The inrushing material hits the newly formed, impossibly dense core and bounces, creating a shockwave of unimaginable force that races back outward. This is the detonation of the core collapse supernova, the star's ultimate self-immolation. The shockwave slams into the star's outer layers, and with energy exceeding what our sun will release in its entire 10 billion-year lifetime, it blasts them into the void. For a few glorious weeks, this single dying star can shine brighter than every other star in its home galaxy combined, a beacon of stellar death visible across the universe. Within that expanding fireball, conditions become more hellish than anywhere else in nature. The temperatures and pressures are so astronomically high that they force atomic nuclei together in a frantic, chaotic rush, forging every single naturally occurring element heavier than iron. The gold in a necklace, the silver in a photograph, the iodine in your body, the uranium that powers reactors, all of it is born in this fleeting, incandescent moment. The supernova is the universe's ultimate alchemist, transforming the simple ashes of stellar fusion into the full palette of the periodic table. This violent scattering is the most important creative act in the cosmos. It is the primary source of the chemical richness that makes our world possible. All the iron in your blood, the calcium in your bones, and the oxygen you breathe was forged inside a star and then hurled into space by a supernova explosion billions of years ago. We are not just living in the aftermath of these stellar cataclysms, we are literally made from their debris. The death of a star is the birth of everything else. The fate of the collapsed core is sealed by its final, crushing weight. If the remaining mass falls between 1.4 and 3 times that of our Sun, the collapse does not stop at a white dwarf. It pushes matter into a state so extreme that atoms themselves are obliterated. Protons and electrons are forced together under pressures we cannot replicate on Earth, merging to become a sea of pure neutrons. The result is a neutron star, a quantum relic forged in the heart of a supernova. All that remains of the star is now packed into a sphere no wider than a city like New York or London. The density is beyond human comprehension. A single sugar cube of this material would not weigh a few billion tons, as if that were imaginable. It would weigh as much as every single person on Earth combined, all crushed into that tiny space. This is the ultimate victory of gravity, compressing matter until it can be compressed no further. But this dead star is anything but quiet. Conservation of angular momentum dictates that as the massive star collapses, its rotation must accelerate, just as an ice skater spins faster when they pull their arms in. A star that might have rotated once every few weeks is now reborn as a sphere spinning hundreds of times every single second. This rapid spin, combined with a magnetic field trillions of times stronger than Earth's, creates one of the most precise phenomena in the universe, a pulsar. The star beams intense radiation from its magnetic poles, and if that beam sweeps across Earth as the star rotates, we observe a regular, repeating pulse of energy, a cosmic lighthouse blinking in the dark with a rhythm more reliable than any atomic clock. The first astronomers to detect these signals nicknamed them LGM for Little Green Men, as the perfect regularity seemed to suggest an intelligent source. We now know we are listening to the heartbeat of a stellar corpse, a city-sized diamond spinning furiously in the void, a monument to the universe's power to create order from the ashes of chaos. That rhythmic pulse from a dead star creates one of the most precise clocks in the universe. But what happens when a pulsar is not alone, when it is locked in a tight, relativistic dance with another dense stellar corpse? This pairing creates a natural laboratory more extreme than anything we could ever build on Earth. As the two massive objects whirl around each other at a significant fraction of the speed of light, they churn up the fabric of spacetime itself, creating ripples known as gravitational waves. These waves carry energy away from the system, causing the stars to slowly, inexorably spiral inward. By meticulously timing the pulses from such a system, astronomers can measure this orbital decay with astonishing accuracy. The observations match the predictions of Einstein's theory of general relativity with near-perfect precision. It is a direct, real-world confirmation of a theory conceived from pure thought a century ago. The steady tick of a solitary pulsar is a marvel, but the subtle changes in the rhythm of a binary pulsar are a whisper from the universe itself, confirming our deepest understanding of gravity, space, and time. This is not just observing a phenomenon, it is having a conversation with the fundamental laws of reality, using a stellar corpse as our messenger. But even the incredible density of a neutron star is not the final word on stellar extremes. Some of these city-sized corpses are born with a truly terrifying attribute, a magnetic field of almost unimaginable strength. These are the magnetars, the most magnetic objects in the known universe. To grasp this power, picture a magnet so strong that it could erase every credit card on Earth from halfway to the moon. Its magnetic field is 1,000 trillion times more powerful than the one that guides our compasses. This force is so immense that it places the very crust of the star under unbearable strain. The solid surface, a lattice of iron nuclei, cannot always withstand the stress. It cracks, these starquakes ripple across the neutron star, and each one is a cataclysm. The cracking crust releases as much energy in a single tenth of a second as our sun will emit in 100,000 years. This energy erupts into space as a blinding flash of gamma rays and X-rays, a scream of pure force echoing from a dead star. In December of 2004, we felt a whisper of this power firsthand. A magnetar 50,000 light-years away, far across the galaxy, released a flare so intense that it actually compressed Earth's upper atmosphere, our ionosphere, from a staggering distance. It was a cosmic event felt across our entire solar system, a direct measurement of a stellar corpse's rage. The story of a magnetar is not one of steady, predictable pulses, but of long, silent periods of pent-up tension punctuated by sudden, violent outbursts. It is a reminder that even in death, the most massive stars leave behind relics of almost incomprehensible fury, objects where magnetic force itself becomes a destructive, universe-shaping power. That steady, rhythmic pulse of a lone neutron star is a testament to cosmic order, but when two of these stellar corpses are caught in a final, fatal dance, they create a different kind of symphony altogether. This is the Kilonova, an explosion born from the merger of two neutron stars, or a neutron star and a black hole. After spiraling inward for millennia, radiating their orbital energy as gravitational waves, the two objects finally collide. The resulting explosion is not as bright as a supernova, but its significance is arguably far greater. It is in this brief, violent embrace that the universe forges its most precious treasures. The collision violently flings out immense clouds of neutron-rich material, a cosmic broth of subatomic particles. In this chaotic environment, neutrons are captured by atomic nuclei at a staggering rate, building up the heaviest elements in the periodic table in a matter of seconds. This is the primary cosmic factory for gold, platinum, and uranium. Before we understood Kilonova, the origin of these elements was one of astronomy's great mysteries. Supernova could not create them in sufficient quantities. The answer was found in the wreckage of dead stars colliding. In August of 2017, gravitational wave observatories detected the ripples from such a merger, and telescopes around the world and in space swiveled to watch. They saw the telltale glow of a kilonova, and its light spectrum confirmed the creation of staggering amounts of heavy elements, including gold, with an estimated mass many times that of our entire planet. This single event produced more gold than has been mined in all of human history. A kilonova is the ultimate act of cosmic recycling. It transforms the cold, dense remains of stellar life into the very elements we value for their beauty and rarity. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that can power a city, all were born in a cataclysmic collision that occurred billions of years ago in the dark between the stars. We wear pieces of these stellar ghosts, carrying a whisper of their final, spectacular encounter with us every day. Beyond the neutron star lies a final, absolute frontier. For the most massive stellar cores, the collapse is so total that not even the defiance of neutron degeneracy can hold it back. When the collapsing core exceeds about 3 times the mass of our Sun, it crosses a threshold from which there is no return. No force in the known universe, no quantum mechanical rule, can counter the overwhelming power of its own gravity. The implosion does not stop. It continues until the core crushes itself out of existence, vanishing into a mathematical point of infinite density known as a singularity. This act of total self-destruction gives birth to the most enigmatic object in the cosmos, a black hole. This is not a physical surface or a solid object in any conventional sense. A black hole is a region of space-time where gravity has become so intense that the very paths that light would follow are bent inward forever. Nothing that crosses its boundary, the event horizon, can ever come back out. Not a particle, not a rocket, not a single photon of light. It is the ultimate point of no return. The star, once a brilliant beacon, has effectively erased itself from the observable universe. Yet its ghost remains, while the black hole itself is invisible, a perfect black sphere against the backdrop of space. Its presence screams its existence through sheer gravitational force. We can see stars orbiting an empty patch of darkness at the center of our galaxy, whirling around nothing at insane speeds. We can observe matter, like gas and dust from a companion star, being pulled into a violent, swirling disk around the invisible object. As this material is stretched and compressed, it heats to millions of degrees, glowing with intense X-rays before it vanishes forever past the event horizon. This is the stellar life cycle's most profound and mysterious finale. It is a transformation so complete that the star ceases to be matter and becomes pure, crushing gravity, a permanent scar on the fabric of spacetime, a silent monument to the ultimate power of collapse. These ghostly stories from across the galaxy do not tell themselves. We must listen, using an entire orchestra of technological marvels to translate the faint whispers of dying stars into a narrative we can understand. Our most familiar tool is the telescope, but modern astronomy is so much more than simply capturing visible light. Giant observatories on remote mountaintops peer into the depths of space, while their counterparts in orbit, like the Hubble Space Telescope, rise above our shimmering atmosphere to deliver crystal-clear images of planetary nebulae and the expanding debris of supernova. Other space-based eyes see in wavelengths invisible to us. The Chandra X-ray Observatory, for instance, does not see the colorful glow of gas. It sees the searing, million-degree heat from the shocked matter around a neutron star or the frenzied accretion disk of a black hole, painting a picture of extreme energy. But to truly understand the chemistry of a star's final breath, we must dissect its light. This is the work of the spectrograph. It takes the gathered starlight and stretches it out into a meticulous rainbow, a spectrum. Within that rainbow are dark lines and bright bars, a unique barcode that acts as a chemical fingerprint. Each element in the universe, whether it is the iron in a supernova's ejector or the oxygen in a planetary nebula, leaves its own unmistakable signature in that spectrum. By reading these subtle patterns, we can determine not just what a distant star is made of, but its temperature, its density, and even how fast it is moving toward or away from us. This is how we know the gold from a kilonova is real, because we can see its specific fingerprint in the light of the explosion, billions of years after it actually occurred. Yet light can only tell us part of the story. Some cosmic events announce themselves through forces far more fundamental. When a massive star's core collapses, the vast majority of the cataclysmic energy is not released as light, but as a flood of nearly massless particles called neutrinos. These ghostly particles stream out from the heart of the collapse, barely interacting with the overlying star. Giant detectors buried deep underground, like Super Kamiok and in Japan, are designed to catch a handful of these elusive messengers, giving us a direct, real-time signal from the heart of a stellar death. And now we can even feel the tremors of the cosmos. Gravitational wave observatories like LIGO and Virgo are not telescopes. They are incredibly sensitive listening devices, measuring the infinitesimal stretching of spacetime itself as massive objects like neutron stars spiral together and merge. This is not astronomy with light, it is astronomy with the very fabric of reality. Each of these tools provides a different chapter, a different sense with which to perceive the universe. The optical image, the X-ray snapshot, the chemical fingerprint, the neutrino pulse, and the spacetime ripple, when woven together, transform a distant point of light into a rich, emotional story of struggle, transformation, and cosmic legacy. These brilliant cosmic explosions were not always distant events in a telescope. They have flared in our own night sky, witnessed and recorded by human eyes. In the year 1054, Chinese court astronomers looked up and saw a new star in the constellation of Taurus, a guest star that shone with a brilliance rivaling the planet Venus. It remained visible even in broad daylight for 23 consecutive days, a silent, unmoving beacon that defied all understanding. This was the supernova that created the Crab Nebula, a cosmic event whose glowing, tangled remains we can still observe today, nearly 1,000 years later. Centuries later, in 1572, the Danish nobleman Tycho Brahe observed another such new star, a supernova now named in his honor. His meticulous measurements proved it lay far beyond the moon, shattering the ancient Aristotelian belief in perfect, unchanging heavens. Just 32 years after that, Johannes Kepler documented his own supernova in 1604, the last such stellar death observed in our Milky Way galaxy with the naked eye. These historical records are far more than just ancient curiosities. They are the first pages in humanity's book of stellar obituaries, a direct, tangible link between our story and the dramatic lives of the stars. Our ancestors saw the same sudden, terrifying light that we now understand as a star's final, creative act of self-destruction. They looked up at the same silent explosion that forged the iron in our blood and the calcium in our bones, and they wondered just as we do. Their awe connects our past to the cosmos in a deeply human way, reminding us that the universe has always been speaking to us, if only we know how to listen. The guest star of 1054 did not simply fade into history. It left behind a ghost, the Crab Nebula, a cosmic storm still raging nearly 1,000 years later. This is not a static monument but a vibrant, living entity. The nebula's delicate, filamentary structure is expanding into space at over 1,000 kilometers every single second, a visible echo of that ancient detonation we can actually measure. But what keeps this cosmic cloud shining so brightly, long after its initial fireball should have cooled and faded? The answer lies at its very heart. There, spinning 30 times a second, is the Crab Pulsar, the crushed core of the star that died. This city-sized neutron star is a dynamo of almost unimaginable power. Its furious rotation and immense magnetic field accelerate particles to nearly the speed of light, flooding the entire nebula with energy. This relentless output makes the Crab a powerful source of light, radio waves, and X-rays, a beacon across the electromagnetic spectrum. To study the Crab today is to watch a real-time laboratory of stellar death. We see how a supernova's shockwave continues to sculpt interstellar gas, and how the intense radiation from a pulsar can illuminate and energize its own expanding tomb. The story written in 1054 is still being written today, a powerful reminder that a star's death is not an end, but a dramatic transition into a new, violently active phase of existence. That theoretical model of a collapsing stellar core met its perfect test in February of 1987. A star known as Sanjulik -69°202 exploded in the Large Magellanic Cloud, a small companion galaxy to our own Milky Way visible from the southern hemisphere. This was supernova 1987A, the closest and brightest supernova witnessed since the time of Kepler nearly 4 centuries earlier. For the first time in the modern era of astrophysics, we had a front-row seat to the death of a massive star. Just hours before the visible light from the explosion reached Earth, something else arrived. Buried deep in mines and under mountains, neutrino detectors registered a sudden, significant burst of these ghostly particles. This was the direct signal from the star's core collapsing into a neutron star, a triumphant confirmation of a key prediction. The neutrinos had traveled almost unimpeded from the heart of the cataclysm, while the visible light was still fighting its way out through the star's exploding outer layers. This single observation transformed supernova theory from an elegant mathematical construct into an observed physical reality. We were no longer just modeling a star's death, we were measuring its final heartbeat. In the years that followed, our telescopes watched the aftermath unfold like a slow-motion film. The Hubble Space Telescope revealed a breathtaking sight, 3 mysterious rings of glowing gas encircling the site of the detonation like a cosmic bullseye. These were not created by the explosion itself, but were instead relics of stellar winds shed by the star in its final 100,000 years of life, now illuminated by the supernova's flash. Then we watched as the expanding shockwave from the blast, traveling at thousands of kilometers per second, finally caught up with the innermost ring. The collision lit up dense knots of gas within the ring, causing them to glow with the ferocious intensity of dozens of suns. It was a real-time demonstration of how a supernova seeds and stirs the interstellar medium, forging new elements and triggering new waves of star formation. Supernova 1987 became our modern Rosetta Stone, allowing us to translate the ancient, violent language of stellar death into a story we could finally understand. It gave a face and a name to a cosmic process, deepening our emotional connection to the idea that we are witnessing the very events that create the substance of our world. That stardust is the very clay from which planets are sculpted. The dramatic deaths of stars are far more than just cosmic catastrophes. They are the universe's essential creative engine. Without the heavy elements forged in supernova and kilonova, the cosmos would be a very different place, a vast sterile sea of hydrogen and helium. There would be no rocks, no water, no complex chemistry. There would be no Earth, but when a star explodes, it hurls these newly minted elements outward, a cosmic farmer scattering seeds of future worlds into the fertile ground of interstellar space. These enriched clouds of gas and dust, now laced with oxygen, carbon, iron, and silicon, slowly coalesce under gravity's patient pull. Our own solar system is a direct product of this cycle. It formed from a cloud that was not pristine. It was a recycled environment, seeded with the chemical legacy of multiple generations of stellar explosions that occurred long before our sun was even a glimmer. Every element heavier than hydrogen and helium in your body, the iron that carries oxygen in your blood, the calcium that strengthens your bones, and the silicon that forms the very ground you walk on, was created in the heart of a dying star. This is not a poetic metaphor, it is a physical, chemical fact. We are all, every one of us, literally made of stardust, the recycled remains of long-dead suns whose final acts of self-destruction made our existence possible. So could life ever emerge from such destructive chaos? A supernova's immediate blast is utterly lethal, sterilizing any existing worlds for light years around. Yet that same destructive force is also the universe's primary source of creation, scattering the essential ingredients for rocky planets and organic chemistry far and wide. The enriched material from a stellar explosion eventually drifts into vast molecular clouds, where gravity patiently gathers it into new stars and new families of planets. These second or third generation solar systems are born with a richer chemical inheritance than the first stars ever had. They contain the iron, oxygen, carbon, and nitrogen necessary to form not just barren rocks, but water worlds and potentially the complex molecules that are the precursors to life. The cataclysm of one star's death directly increases the potential for biological complexity in the systems that follow. Our own Earth is a product of this cycle, a world built from the ashes of long-dead giants. But what about the planetary systems that form directly around the stellar corpses themselves? Could life cling to existence in such hostile environments? We now know that planets can indeed orbit the dead cores of stars. The first planets ever discovered outside our solar system were not found around a sun-like star, but orbiting a pulsar, a rapidly spinning neutron star. These pulsar planets exist in an environment of extreme radiation, bathed in constant, deadly X-rays and gamma rays from their furious parent. For life as we know it, this would be a nightmare landscape. Yet the very existence of these worlds forces us to expand our imagination. If a planet had a thick enough atmosphere or a global, subsurface ocean, could it shield any potential life forms from the relentless bombardment? It seems unlikely, but the universe has repeatedly surprised us with its resilience. The emotional narrative of stellar death is thus transformed. It is not merely an end, but a violent, necessary step in a grand cycle of renewal. The destruction of one star sows the seeds for countless future worlds, and perhaps in the most unexpected corners of the cosmos, for new beginnings in the most extreme environments imaginable. This cosmic cycle of stellar life and death holds a profound emotional weight, a mirror reflecting our own reality. We are surrounded by stories of permanence in our daily lives, but the universe whispers a different truth, one of constant, beautiful transformation. Stars, in their majestic arcs from birth to oblivion, live by the same immutable laws that govern our own brief moment in the sun. They are not eternal. Our own sun, the steady anchor of our solar system and the source of all life on Earth, has a definitive expiration date. Billions of years from now, it will exhaust its fuel and swell into a red giant, a fate that adds a layer of deep poignancy to our existence. We are living our lives under a star with a known, if distant, end. This knowledge can feel overwhelming, yet it also evokes a powerful sense of awe and a humbling perspective. We are tiny, fleeting creatures on a small rock, witnessing giants live and die in the heavens. But this is not a story that should make us feel small or insignificant. Instead, it forges a strange and beautiful kinship with the cosmos. The iron in your blood, the calcium in your bones, every atom that allows you to draw breath and contemplate the stars, was forged in a cataclysm like the ones we have witnessed across the galaxy. Your very existence is a direct consequence of stellar death. This transforms the narrative from one of distant tragedy to one of intimate connection. We are not just observers of this grand, dynamic, and impermanent cycle. We are active participants made from its remnants, living proof that endings in the universe are very often beginnings in disguise. Humanity has always looked to the stars and seen its own reflection. Long before we understood the physics of a supernova, we wove their sudden, brilliant appearances into our myths and legends. A new star flaming to life in the familiar tapestry of the night sky was rarely just a celestial event. It was an omen, a portent of a king's death or the birth of a great hero. In some cultures, these cosmic flares were seen as dragons clashing in the heavens, or as the fiery tears of grieving gods. These stories were our first attempts to make sense of the terrifying and beautiful violence occurring in the great dark, to find a human-scale narrative within the impersonal mechanics of the cosmos. That instinct to connect has never left us. It has simply evolved. In modern times, the dying star has become a powerful fixture in our science fiction, a narrative device rich with meaning. The gentle, melancholy star in The Little Prince, which the prince must protect, is a poignant metaphor for caring for something fragile and beautiful in a vast, uncaring universe. In contrast, a supernova in Star Trek might be a weapon, a navigational hazard, or a spectacle of pure cosmic power, representing both the destructive and awesome forces that humanity must learn to navigate. The emotional resonance is unmistakable. We see in the star's struggle a mirror of our own. Its stable life is our period of peace and growth. Its red giant phase is our own middle age, a time of transformation and swelling influence. Its final, brilliant supernova is our own mortality, a death that scatters the pieces of our life to enrich the world we leave behind. This is not just a fanciful comparison. It is a deep, psychological recognition that we are part of the same cycle of impermanence and renewal. Artists and musicians continue this tradition of translation, turning data into emotion. Painters study the ethereal shapes of planetary nebulae and try to capture not just their form, but their feeling of sublime release. Composers listen to the rhythmic pulses of a pulsar, translated into sonic frequencies, and weave those cosmic heartbeats into symphonies that thrum with the rhythm of the universe itself. They are not merely illustrating astronomy, they are interpreting the soul of the cosmos, giving voice to the silent, emotional stories written in light and gravity. When we stand before a painting of the Crab Nebula or lose ourselves in a symphony inspired by stellar collapse, we are not just observing science, we are feeling it. We are connecting with the universe on a deeply human level, acknowledging that the same forces that govern a star's glorious death also shape our own stories of struggle, legacy, and letting go. Our own sun will one day become a red giant, transforming the sky above Earth into a terrifying, beautiful inferno. This is not a science fiction scenario, but a scientific certainty written in the laws of physics. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core. The delicate balance that has held for billions of years will break, and the star will swell to over 200 times its current size. Its outer atmosphere will stretch outwards, a slow, creeping tide of fire. The inner planets, Mercury and Venus, will be swallowed whole, vaporized in an instant. Earth's fate hangs in the balance. While it may not be fully engulfed, its proximity to the bloated star will be its end. The oceans will boil away, the atmosphere will be stripped by the solar wind, and the very rocks will melt into magma. The world that nurtured life for eons will become a scorched, barren rock, orbiting inside the outer fringes of a dying star. This is the future of our solar system, a clock that began ticking the moment the sun ignited. After its red giant phase, the sun will have one last beautiful act. It will gently expel its outer layers into space, creating a vast glowing shroud, a planetary nebula. For tens of thousands of years, this cosmic cloud will be visible from distant star systems, a final, ephemeral work of art. And at its heart, the sun's core will remain, collapsed into a white dwarf. This Earth-sized ember will contain almost the entire mass of our star, a diamond-like cinder that will glow with residual heat for trillions of years, slowly fading into cold and darkness. This entire cycle, from stellar nursery to white dwarf, is the same story we have witnessed across the galaxy, but this time the star has a name. It is our sun. This knowledge transforms the grand, impersonal cosmic cycle into something deeply personal. It is the definitive future of our home, a story in which the legacy of our planet and every human achievement is intrinsically entwined with the life and death of our parent star. We are living our lives under a temporary sun, a truth that lends a profound and poignant weight to our fleeting, brilliant moment in its light. Yet for all our advanced knowledge, a crucial secret remains locked inside that catastrophic collapse. We know the core of a massive star implodes to form a neutron star, but what exactly unleashes the rebound shockwave that tears the rest of the star apart? This is the supernova trigger problem, and it is one of the most stubborn puzzles in modern astrophysics. Our most sophisticated computer simulations often fail. They show the initial shockwave stalling just a few hundred kilometers out, unable to push through the overwhelming weight of the star's infalling outer layers. The star, in these digital models, simply fizzles, collapsing directly into a black hole without the brilliant supernova we know must occur. So what is the missing ingredient, the final cosmic push that revives the shock and allows the star to explode? The leading suspect is the ghostly neutrino. In the heart of the newborn neutron star, temperatures are so insane that trillions of these nearly massless particles are created. They flood outward, carrying away immense energy. The prevailing theory suggests that a small fraction of these neutrinos, perhaps just 1%, deposit their energy just behind the stalled shockwave, reheating it and driving it outward like a cosmic bellows. But is this neutrino heating enough on its own? Other forces may be at play. Intense magnetic fields, twisted and amplified by the core's frantic rotation, could focus the explosion into powerful jets, punching their way out like blowtorches. Or strange quantum effects deep within the neutron soup of the new core might provide an extra jolt of energy. The truth is, we do not yet know the exact recipe. This unsolved problem means that every supernova we observe is a natural experiment, testing a theory we cannot yet fully replicate. It is a humbling reminder that even in death, a star's final heartbeat is a complex, turbulent process that still challenges our most powerful computers and brightest minds. The quest to solve this mystery is a dramatic race, a story where the universe holds the final answer, and we are still learning how to ask the right questions. Even our most precise cosmic yardsticks have a shadow of uncertainty surrounding their birth. The Type Ia supernova, that brilliant standard candle we use to measure the universe, comes from a white dwarf crossing a critical mass. But what exactly pushes it over the edge? Astronomers are locked in a cosmic detective story, trying to identify the exact culprit system that triggers this cataclysm. The leading suspects are two. The first scenario involves two white dwarfs locked in a tight orbital dance. Over eons, they radiate gravitational waves, spiraling closer and closer until they finally merge into a single, overweight object that instantly detonates. The second suspect is a different kind of partnership, a white dwarf and a living, bloated red giant. The dwarf steadily siphons material from its giant companion, greedily accreting mass until it reaches that same explosive limit. Each of these scenarios would leave behind a different kind of crime scene. A merger of two white dwarfs might be a more violent, asymmetrical event, while accretion from a red giant would likely be preceded by specific chemical signatures in the surrounding space, traces of the material stolen from the companion star. The problem is, we have never definitively caught a star system in the act of becoming a Type I supernova. We see the brilliant explosion, but by the time the light reaches us, the progenitor system has been utterly vaporized, the evidence destroyed in the very blast we are studying. This is not just an academic puzzle. The consistency of these supernovae as standard candles is the bedrock of our measurement of cosmic distances and the discovery of dark energy. If there are multiple ways to make one, and each path leads to a slightly different intrinsic brightness, then our cosmic map becomes blurred. Our most fundamental tool for understanding the universe's expansion depends on solving this stellar mystery. So the hunt continues, with telescopes scanning nearby galaxies, searching for any binary system that looks like it could be a pre-supernova, any telltale sign that might whisper which path a star takes to its precisely timed doom. The death of a star sends a powerful shockwave racing through the surrounding cosmic environment. This is not just a final act of destruction, but a creative pulse that travels for light years, slamming into cold, dormant clouds of gas and dust. The immense pressure from this collision squeezes these nebulae, overwhelming their internal forces and triggering a gravitational chain reaction. The cloud begins to fragment and collapse, igniting the fires of nuclear fusion and giving birth to a new generation of stars. The Orion Nebula, that vibrant stellar nursery, is likely a product of such an ancient cascading death. This cycle transforms stellar death from a solitary end into a cosmic catalyst, where one star's demise directly midwives the birth of countless others. These shockwaves also carry immense heat, warming the vast, cold spaces between the stars. This heated interstellar medium becomes resistant to collapse, temporarily putting a brake on star formation in that region. On an even grander scale, the combined fury of many supernovae in a galaxy can create a colossal galactic wind, a hurricane of energy and matter powerful enough to blow vast reservoirs of star-forming gas clear out of the galactic disk. This process actively regulates a galaxy's growth, preventing it from burning through its fuel too quickly. The brilliant, short-lived lives of the most massive stars and their violent deaths therefore act as a galactic feedback mechanism. They are the invisible hand that shapes the pace of star birth, the distribution of elements, and the very structure of the galaxy itself. From this ecological perspective, our own Milky Way is not a static collection of stars. It is a dynamic, breathing ecosystem, an immense engine powered by the continuous cycle of stellar life and death. Every supernova we observe is not merely a distant fireworks display. It is a heartbeat in the life of a galaxy, a transformative force ensuring that nothing in the cosmos is ever truly wasted. But the crushing force inside a neutron star might not be the final word. What if the pressure grows so immense that even the neutrons themselves cannot hold their structure? Theoretical physics proposes a state of matter so extreme it makes a neutron star seem almost ordinary. This is the hypothetical quark star, an object where the neutrons are utterly dismantled. In this ultimate crucible, the subatomic particles that form protons and neutrons break down into a seething, primordial soup of their fundamental constituents, quarks. This would create a form of matter that does not exist stably anywhere else in the universe, a single, city-sized droplet of pure quark matter. Some theories even suggest this soup could stabilize into an even stranger form, a strange star made of so-called strange quarks. The search for these objects is one of the most tantalizing pursuits in modern astrophysics. We may have already seen candidates like the object known as RxJ 1856, which appeared slightly smaller and denser than a neutron star should be, or the incredibly massive pulsar Pulsar J0348 plus 0432, whose weight might be just enough to crush its core into quarks. Yet, definitive proof remains elusive. Confirming a quark star would be like discovering a new element on the periodic table, but for the fundamental forces of nature itself. It would open a direct window into the laws of quantum chromodynamics, the rules that govern how quarks interact under conditions we can never hope to recreate on Earth. This quest pushes the emotional story of stellar death from the observable into the deeply theoretical and bizarre. It asks what happens when matter is squeezed beyond even the most exotic state we know, forcing us to confront the ultimate limits of existence itself, where the corpse of a star becomes a laboratory for the universe's most fundamental secrets. The legacy of a star's death reaches far beyond its own galactic neighborhood. When a supernova detonates, its fury can be so immense that it blasts newly forged elements clear out of the galaxy's gravitational grasp. These enriched clouds of iron, oxygen, and carbon are hurled into the vast, dark emptiness of intergalactic space, riding colossal winds generated by countless stellar explosions. This material does not simply vanish into the void. It enters the cosmic web, the vast, filamentary structure of the universe where galaxies are strung like pearls on invisible strings of dark matter. Drifting for billions of years, these ancient stellar ashes are eventually captured by the gravitational pull of a different, distant galaxy. The very atoms forged in one stellar forge can thus become the building blocks for new stars and planets in an entirely separate island universe. This is intergalactic recycling on the grandest possible scale. It means that a single carbon atom created in the death throes of a star in a galaxy far, far away could have traveled across the cosmic dark to eventually find itself part of a living cell on a world like Earth. Our local story of stellar life and death is not just a galactic tale. It is a universal one. Every galaxy is connected to every other through this slow, majestic exchange of elemental gifts. The emotional journey of a single star expands to a cosmic scale, its final breath contributing to the chemical enrichment and the potential for life across the entire observable universe. Your body is a collection of ancient stories written in stardust. Every single atom within you that is heavier than hydrogen or helium carries the legacy of a stellar death. That nitrogen and oxygen filling your lungs with each breath was forged in the heart of a supernova billions of years ago. The carbon that forms the intricate backbone of your very DNA was created through the fusion process inside a red giant star, a star that lived and died before our own sun even ignited. This is not a poetic metaphor or a flight of fancy. It is the established chemical truth of our existence. We are literally walking archives of the cosmos. The calcium that strengthens your bones, the iron that carries oxygen in your blood, the phosphorus that powers your cells, all of it was synthesized in the final, desperate moments of a star's life and then scattered across the galaxy. This profound connection transforms every stellar story we have witnessed from a distant astronomical event into a deeply personal origin story. The cataclysmic death of a star is not just something that happens out there. It is the very reason you are here. We are the universe's way of remembering itself, a collection of atoms that have coalesced into consciousness, now looking back at the stars and finally beginning to understand where we came from. This grand cosmic story of transformation and renewal reveals a universe far more dynamic and interconnected than the silent, static sky would suggest. The gentle fade of a white dwarf, the brilliant flash of a supernova, and the violent merger of neutron stars are not final endings. They are necessary transitions, the very engines that forge the elements for planets, for life, and for consciousness itself. These stellar deaths teach us profound lessons about impermanence and resilience, echoing the cycles we see in our own world. They offer a humbling perspective on our own small, yet significant, place in this vast cosmos. As Carl Sagan so beautifully expressed, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, were all made in the interiors of collapsing stars. We are made of star stuff. Let this knowledge not overwhelm you, but instead inspire a deep and lasting awe, a driving curiosity to look up at the night sky and understand your own connection to the lights above. If these emotional stories from the edge of existence have moved you, we would love to hear which part resonated most. Share your thoughts in the comments below and subscribe for more journeys into the heart of cosmic mystery.